Imagine we're involved in the manufacturing of aspirin. Every day a new batch of material is made. We can measure some data about the production and plot it on the day it was made. We can include data such as purity, mass of the material made, starting material, the operator and the machines that were used to make the material. We continue to plot this each day and visualize the data. As we continue to produce more batches, we see the set of data is slightly different from the others. This is what we call process variability. Process variability is the natural or inherent changes that occur in the output of a manufacturing process. In our aspirin production example, factors like variations in raw material, minor fluctuations in temperature or pressure in the process, or even the precision of the measurement of the instruments can cause this variability. Understanding and managing process variability is crucial in manufacturing. It helps us ensure the quality of our product, and in this case, the purity of our aspirin, that it stays within acceptable limits. Let's introduce a line on this chart. The line represents the mean or the average of all the data points we've collected so far. As we produce more batches, we continue to calculate the mean. This gives us a sense of the central tendency of our process. Next, we add two more lines. These are our control limits. The upper control limit and the lower control limit define the range within which we expect to find our process to operate under normal conditions. Together, the dots, the mean line, the control limits form what we call a control chart. A control chart helps visualize process variability, monitor changes over time, and detect issues in the process. If a dot falls outside the control limits, it signals that there may be a problem with the process that needs investigation. Let's try an example of a control chart. This one was obtained from Dr. Steph Powers. This is her website here that we can take a look at. You can go to later. But she provides a data set. That's what I wanted. And she can go through a variety of different types of control mechanisms. But the one we want is the control chart. So using this data set, we're going to call this into Python and follow what she's done. Inherently in most of the libraries that are available for statistics within Python, there's not one method that actually can create a control chart. I'm not familiar if Seaborn can do that. It possibly can, but this is the process that we're going to go through to develop a control chart. Let's say we have four samples. This could be four different batches on different days. It could be a variety of different things, temperature readings over time. But anyway, it's four different samples, and here's the data set for those sample one, sample two, sample three, sample four. And we can have them indexed. So we're going to call them into a data frame here, index them from 1 to 19 or 0 to 19, so 20 data points. And we can see that each day potentially or each index, here's the four samples for that one index or say that one day. So if this was day 0, we took four readings and here's the readings. And on day 1 or 2, we took these readings and so on and so forth. So each row here represents four samples that were taken during the course of that day. Um, when we're going through this, we need for a control chart, then we need the mean of the data and we need the upper and lower control limits. Now, the upper and lower control limits statistically typically are determined by 3 times the standard deviation of the mean. So if we can calculate the mean down here like this, and we can obtain the standard deviation of it as well, for the upper and lower control limits, we'll just go 3 times that. So we'll create a couple of variables here. One's called global average, so the average mean of the data, the standard deviation of the actual average data, and the upper control limit here, they've got it defined as 2 times the standard deviation. Typically in industry, it's about 3 times. You can, but this is arbitrary, and it can be changed. So these dotted lines that get produced here can be changed depending on the output. If you're working for GE Six Sigma, it is 6 times this standard deviation is what they're looking for. But in most industries, they'll start off at 3 times the standard deviation, get these control lines. try to figure out what's going on with the data, continue their batch process or continuous process, monitor variables and see what happens. If they can now introduce new changes, we can change the standard deviation, we can get that to be tighter over time, and then therefore we can start to introduce tighter restrictions, go further standard deviations up to 6 sigma that GE, for example, wants to do. So now that we've got our data set, we've got our global average and standard deviation, we've determined what our upper and lower control limits are based on these equations. So we've got these variables created. We now have to plot everything. So using matplotlib, that I assume is up here, we are going to now create horizontal lines. So that's what this does. It says create a horizontal line based off this value. The color will be black and it will be dashed. So using this value that gets obtained from this calculation, we're going to create the upper control limit here. A horizontal line for global average, so that will be the mean right here, and we put it here. We could have it as a solid line. We could change the color to red if we wanted to. And we'll do a third horizontal line. That's the lower control limit. And so now we can visualize our data set. So we're going to now place our data set right here. So that's where this plot is. So PLT plot. So the average data, and we're going to treat it as a little O or a circle here like that. That's why it comes out like that. No line style. If we had a line style or if we didn't indicate, it would actually draw a line in between all of these and it would look not so good. So we want to actually have no lines for now. And now that we've got all the information on here, we can actually take a look. Oh, we're going to plot as well day versus hundreds of an ounce over 16. This is for a catch-up example. And so we're going to see what's in spec. So these are all within specifications based off of 2 standard deviations. And this one here is outside of the spec. If we were to change this, we can see that our control chart might actually change. And what we can do here is try to run all the cells again and see if our control chart changes and if our value ends up within that. And so now when we changed our 3 standard deviations, you can see that this is within control now, considering we wanted 3 standard deviations. So again, this is not arbitrary, but this is the value that you can change to change these levels of the control charts depending on what type of system you've got. And I said in industry, typically 3 standard deviations is the starting point for starting to monitor your process. You can also now print out the global average, the standard deviation, the upper and lower control limits that are calculated. So these are right here. And we can actually change the plot too. So we're going to keep the same upper and lower control limits, but we can change the samples. So we can actually show that these some dots are coming from sample 1, some dots are coming from sample 2. And so we can actually plot just specifically sample 1 data with this type of marker, and we can change the color of them. So eventually here we can change the colors. So upper control limit black, so anyway, so here, and the colors are changing. Hmm. It's not that the colors are changing, it's that we're actually plotting different samples, so it's automatically changing the colors of each one of these. So that's why you're getting this sort of different color change here. And so it's just a really simple way of creating a control chart. We plan on doing it with our data as well, so we're going to try this example here and use it on our own. So here is a control chart using our set of data. So we've called in a data set called a control chart. If I were to go down here and show the data. So what I've done is I've taken the same data set we've had before, massive salicylic, acetic anhydride, and whatnot. But what I've done is for each index here, I've actually applied a day. I randomly created days. I don't know the exact days that were done, but I just wanted it for this data set for us. So we have a day running from 2017, January 1st, I believe, or so, all the way up to January some odd in 2023 right there. So November 19th, 2023. And so now we're going to take this data set, we're going to organize it and plot this for the entire since start of 2017. So we're going to bring in pandas so we can bring in the CSV file as a data frame. We're going to plot it with matplotlib. So we're bringing in the data frame with the PD read CSV. We're creating the data frame based on the day. So now that we've got day here is actually our date. And so based on day, we're going to create the data frame and we're going to introduce something new. This is called date time. So this is a library that's used. We don't have to call it in, it's inherent in here. And we're going to change day, the properties of day, because right now this is a string essentially, and we're going to change it into date time, which it makes it manageable for the pandas data frame to organize it as real numbers essentially, not as a float, but as date time. So we're going to now calculate the mean and the standard deviation. These are required to get our median line here, right here, or sorry, our mean line, and the standard deviation so we can determine whether we are going to go 2 or 3 or 2.5 or 6 sigma, 6 standard deviations. We're going 3 sigmas with it or 3 standard deviations. So now we're going to create the control chart. So we're going to create a figure. So plot size 10 by 6, that's the box. We're now going to plot the actual data. So on the day uh, column, all the mass is salicylic. Give it the label mass salicylic, have a marker of a dot here like this, and no lines, please. Now we create the 3 horizontal lines. The first one for the mean, the second one for the upper control limit, and the third one for the lower control limit. Once we have those plotted, now we can put in the label down here for the day. We can put in mass salicylic acid as the X label. We have a title control chart for mass salicylic, and we can create our legend here so we know what's what, and we'll plot it. And we can see here now we got a large set of data. Most of it, the central tendency happens to be around 5 grams. That's the mass of salicylic acid that we expect students to weigh out. And each one of these dots now represents an individual student's work. So it's a huge amount of data that we can plot over time. This missing spot right here obviously was during COVID, so we weren't able to actually produce anything. But here we can do a run chart and see overall what's the central tendency for the students to do the work. We can see some massive deviations here that we've seen in the past. But this is how we develop a control chart, and it allows us now to visualize things like what are out of control. And now in order to actually figure out what these dates are or what these dots are, if we have hundreds of thousands of data points, we can start to do calculations to try to figure out what are these values? What are the plots outside of the mean? So now that I know that the 3 standard deviation here, I've got a calculation, there's my standard deviation. I can go back to the data frame here and I can apply on the day what values of mass salicylic acid are greater than 3 standard deviations, what masses of salicylic acid are less than 3 standard deviations, or the mean minus 3 standard. And so I can figure out what these 3 data points are and what these 2 data points are without having to just eyeball this entire data set and try to figure it out. So I can go through and use the Python calculations to actually help me visualize what that data is. So we've done that. If we scroll down here, I can print out the mean that was delivered. I can print out the standard deviation here. And so now I will create 2 new variables. One's called the upper bound and one is called the lower bound. And I'm going to use these to identify what our outliers are. So to identify our outliers then, outliers, a new variable, will now be anything in the data set from the mass of salicylic acid column that is greater than the upper bound, and so the upper bound is defined as this. And in the column mass of salicylic, anything lower than the lower bound. So, and that is the lower bound. And so when we print this out, we should get, hopefully, we have 1, 2, 3, 4, 5 data points that are out. 1, 2, 3, 4, 5. And what's nice is it actually tells us what year and the day that it was done. We can actually visualize the mass of salicylic, but we can also call in the rest of the data that goes with it. So there's our 1, 2, 3, 4, 5 data points. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so this is the info that the calculation was based on here with mass salicylic, and all the rest of the data comes with it. We don't have to bring that data, but it's useful because we can see now this operator on this day This is the outcome. Here is all the other process parameters that were involved in that day. And now we can start to see problems that could have occurred or figure out how do we figure out the problem? How do we determine what happened on those days?